Now yesterday, when we looked at what an action potential looks like on a graph, I labeled something called the refractory period, where I couldn't have a new impulse. And one of the things that's useful about there being a space between impulses is that your nervous system can detect how often there's an impulse, which will really play into this particular idea. Now, when we're talking about action potentials, it's called an all or none response. When we say that, what we're really saying is we get the same size of action potential, or none at all. So there's not tiny action potentials, medium action potentials, big action potentials. Either there's an action potential, one size fits all, or there isn't. So there's a little table here just to kind of illustrate this idea for you. Let's say we were providing a stimulus to a neuron. We'll just call it an electrical stimulus, like we were shocking it. And we progressively increased the stimulus. We'll look at the membrane potential to show where depolarization happened and what occurred as we increased the strength of the stimulus. So for fun, let's just say that 3 millivolts is the threshold. I made that up. This is fake made up, fake stuff, but we need to know what the threshold is so that we can illustrate things. If I have a neuron and I apply a stimulus that's below the threshold, the membrane will stay at -70 millivolts. It will stay polarized. Nothing will happen. It's not enough to open those voltage-gated sodium channels, and so the membrane stays where it is. If I increase the stimulus to 2 millivolts, still wasn't enough, and the membrane stays at its resting membrane potential. But if I get to 3 millivolts of stimulation, which in my fake made-up neuron I decided was the threshold, my neuron will depolarize completely and get all the way up to +30 millivolts. If I increase the stimulus, so I make a stronger stimulation to the neuron, what will happen during my action potential? It will get up to +30 millivolts. If I make it even stronger, what will happen? Still, my action potential will get up to +30 millivolts. So if I look at this data, there was no action potential in the first 2 scenarios. In the other 3, even though the stimulus was getting stronger and stronger and stronger, if I looked at my action potential on a graph like we did yesterday, it would look the same in all 3. It would be the same size. So it wouldn't get bigger as I got to 4 millivolts. This action potential is what you would see in all 3 of those scenarios that were past the threshold. So if the action potential can't get bigger, how on earth would you know that one sound is louder, or that one cup of coffee is hotter than the other, or that one light is brighter? How would you detect that? It'll all be about frequency. The frequency increases with the stimulus strength. So if I were to take this same bit of data that I had here and just make a quick little sketch of a graph of how it would look, I could have my stimulus down here and the frequency of impulses along the side. By frequency, we mean how often, how many impulses are we getting. Here's my 1, 2, 3, 4, 5. Now, with the 1 or the 2 millivolt stimulus, I was getting no action potentials. So I'll make it extra thick, but I mean my line would be on the x-axis. I was getting 0 impulses. As soon as I got to the stimulus of 3, I started getting impulses. When I got to 4, it would increase. When I got to 5, it would increase. So even though the size of the action potential won't change, the number of action potentials in a particular amount of time would increase. So your brain needs to be able to detect the beginning and end of an action potential. It's another reason you need the refractory period. So there's a distinct division between one action potential and the next. There would, of course, be a limit to this. You cannot detect an unlimited amount of action potentials. There'd be a point where you're at your limit. You're at your maximum. It's the biggest thing that you can detect, but it would go pretty high before you would get to that point. So, if a question ever asks you, what will happen if the stimulus is stronger, you will never pick the action potential will get bigger. You'll never say that because it won't. They are one size fits all. Now, the values that I've given you here are for the average neuron. And remember, not every neuron is identical, but if I were to take one neuron, it will have the same threshold, the same resting membrane potential. It might not have the same one as another neuron, but for every neuron, this would be true. Its action potentials would not change size. Does anyone have questions about that? So if we're talking about the propagation of an action potential, there are 4 words that come into play. And I put a nice picture there that illustrates some of this stuff. So the words are on your handout. I'm just going to switch to the page that has the pictures so that we can look at it. Now, the first thing I said about propagation for an action potential is that it is non-stop. I don't know how to explain that other than it doesn't stop. There's no pause. It keeps going until we get to the end. So for that first point of non-stop, we're talking like this. There's no pause in the conduction of an action potential. If it starts traveling down the length of the axon, it will go all the way to the end. The only thing that could change that is if the axon was damaged and there was physical damage to it and it couldn't transmit it, but otherwise there is no mechanism that would stop the action potential. The other thing is that it goes in one direction, and in a couple of the animations we watched yesterday, they talked about that. This is the one direction. It always goes from the soma to the axon terminals. Always. It does not go the other way. Now, the reason it doesn't go the other way has to do with that refractory period. Because the membrane is extra negative, it can't depolarize where it just got depolarized. It has to move in one direction. Now, if we take a look at what's happening, I say that it's saltatory, and that's what this little part is indicating, where we have point A and point B. In a myelinated neuron, this is what conduction would look like. So if we took a piece of the axon and zoomed in on it, large segments of the axon are completely covered with the myelin sheath. So this is myelin over here. Myelin is an insulator. Notice how there are no voltage-gated sodium or potassium channels. There's no sodium-potassium pump. There's nothing there that would let ions go in and out of the cell membrane, so there can't be an action potential there. So here's what happens. If we start at point A, we have an action potential happening, just like it says. Because there's an action potential, a whole bunch of sodium has rushed in. So if you follow the arrow, sodium is coming in. And notice how it's coming in on both sides of the axon. we typically will look at one side of the axon, but remember, there isn't just one channel. There's not just one sodium-potassium pump. There are a whole bunch of them all over the place. Now, sodium rushes in, and it's not just going to sit there and hang out and hope that something happens. Sodium, as you can see right here, diffuses. Now mine has a bit of color shading, which I can't always replicate on the things that I give you. But if you notice near point A, the color and the shading is like this dark yellowish color. That's to represent that there's a lot of sodium at that point. Because of diffusion, sodium will naturally move to a place where there's less of it. So sodium diffuses to the next point. That sodium diffusing to the next point, so this spreading current, will help bring the membrane at the next node to threshold. So one action potential happened, a bunch of sodium rushed in, but it didn't just sit there. Imagine it was like a water slide, it just kept on moving down the path, and that was enough to hit the threshold of the next section of the membrane. Then its channels would open and sodium would rush in there. It would diffuse down the axon and so on. And it would continue in that direction in a saltatory way, always having action potentials at the nodes. So in between those sections of myelin sheath that are covering the axon, there would be an action potential. Now, does anyone want to ask anything about the fact that it is nonstop, one direction, and saltatory? Okay, the last one is the disorder. If a person had MS, that involves the destruction of myelin. If myelin were to be destroyed on a neuron that normally has myelin, it means that we can't have saltatory conduction anymore. And if you remember from the chart we made, neurons that were myelinated had faster impulse conduction than neurons that weren't. So in MS, so I guess I should say this is multiple sclerosis. A person's myelin sheaths are getting attacked often by their own immune system. Now that's just an example. I mention MS because it comes up frequently in exam questions where they say, hey, here's what happened to this person. What would happen to nerve impulse transmission if the myelin sheath were damaged? Now that's the official end of lesson 3, but lesson 3 and lesson 4 really go together. Lesson 4 is about the synapse, which is at the end between one neuron and the next. And it's really part of our discussion of impulses. So you have this little diagram here with a bunch of pieces in it, and we're just going to talk about some of the structures that make up the synapse. Now the picture that I've given you here is really zoomed in. So I'm just going to quickly sketch out what this is. So what we are looking at in this little diagram here is this little space. The space between the axon terminal of one neuron and the dendrites on the edge of the next one. So it would be really probable and reasonable for there to be a picture of a synapse. I know that in the exemplar questions that I gave you in a big booklet, there's one. On the quest that you'll do next week, there's definitely one where it's a picture and you have to identify what's going on. So there are some terms that you need to recognize about a synapse. First, you need to recognize that this neuron is called the presynaptic neuron, and this one down here is the postsynaptic neuron. Now you'll know which one is which because there will be lots of other visual cues. This is typically the shape that you'll see. The presynaptic neuron will look, for lack of better explanation, I think it looks like a dinosaur foot. So imagine cartoon dinosaur, big brontosaurus. I think that's what its foot looks like. The other side will usually look pretty flat. Even though dendrites are these branch structures, if you zoom in really close on them, it'll usually look like a pretty flat looking surface. Pre means before, post means after. So you need to be able to use those terms confidently because sometimes that will be the difference between the correct answer and an incorrect answer. Now in the presynaptic neuron, you should be able to see synaptic vesicles. Synaptic vesicles contain molecules that are called neurotransmitters. So if you remember, we said the length of the axon, the length of the neuron, it's an electrical impulse. But as soon as we get to the synapse and one neuron is going to contact the next one, we're not using electricity anymore, we're using a substance. This is the substance. These synaptic vesicles should be your big clue about which one is the presynaptic and which one is the postsynaptic neuron. So shape aside, the one that has a whole bunch of vesicles in it has to be the presynaptic neuron. Now, if you take a look at what's happening, all of these little round things are synaptic vesicles. Right here and right here, you can see a vesicle fusing with the membrane. So this is exocytosis happening. You would have learned about exocytosis in Science 10, but in case you've forgotten, it's when a vesicle or any membrane-bound structure moves towards the membrane of the cell that it's in, fuses with the membrane, and then empties its contents outside of the cell. This is where we have the release of neurotransmitters, which I'll just represent with N and T, into the synapse. So on this particular picture, it says that each of these little dots is a neurotransmitter. But if it didn't, you should recognize that the stuff that came out of the vesicle, those are neurotransmitters. Now, does anyone have questions so far? Okay. If we look over here, we have the word synapse. Sometimes it will be referred to as the synaptic cleft, which is literally the space that is between the two neurons. On the postsynaptic neuron, there should be some sort of structure where the neurotransmitter can attach. The way that that gets drawn is different all the time. Sometimes it looks like a little space or a little hole that it can fit in. Sometimes it's a little piece that sticks out. But there should be something on the postsynaptic neuron's dendritic membrane where the neurotransmitter could go. So in this one, it looks like it's a little hole that it can go into. Sometimes instead of that shape, you might see something, and I'll just pick a different color, but you might see something that looks like almost a little box that could hold it where the neurotransmitter could go into it. The way that we draw these varies vastly, and you'll see a bit later on, I have another picture where it's represented a different way. But there should be something that the neurotransmitter can attach to. It's excitement across the hallway, hey? Now, does anyone have any questions they want to ask about any of that stuff? So then here's my question. Where do you think those neurotransmitters go? Action potential happened, they got released, then what? They bind to the receptor, then what? They make something fire, sure, but where do they go after? So they bind it to they were bound to the receptor, they made something happen. Where are they going to go after? What do you think? She's right so far. Those are all the things that are going to happen. So here's what happens. Once the neurotransmitter has bound to the receptor and the action potential has happened, they're not going to hang around. If they stay in the synapse, you're just going to keep having action potentials over and over and over again, and your nervous system would start going crazy. So these neurotransmitters go through a reuptake process. They'll be out in the synapse for fractions of a second, then the presynaptic neuron will take them back so it can use them again. Reuptake. Now, all of this requires energy, and so while this is not our main topic, hopefully you can see that there are mitochondria, and it's there because this whole process requires a ton of energy. Energy to release the neurotransmitters out into the synapse, energy to take them back when the action potential is over. So, if we could summarize, and Alex did a good job of this already, what would happen, here's the events that would happen that would cause things to change. We would get an action potential in the presynaptic neuron. That action potential, when it arrived at the axon terminal, would stimulate exocytosis of neurotransmitters. The neurotransmitters would go into the synapse. The neurotransmitter binds to the postsynaptic neuron, and then neurotransmitter reuptake. That's basically what would happen in order in a synapse. Now, this is the most simplistic version of this explanation. There's a lot of chemical stuff that happens that causes this to occur, but very basically, this is the sequence of events. Now, when I asked what happens after the neurotransmitter binds, she said something happens in the postsynaptic neuron, and she's right. Something happens, but what exactly is going to happen depends on what the neurotransmitter does to the postsynaptic neuron. So our next little thing is to compare neurotransmitters because some of them will stimulate things and some of them will inhibit things. So we're going to elaborate on this point here. So before I do, does anyone want to ask anything there? Okay. So there are excitatory and inhibitory neurotransmitters. They do different things once they attach to receptors. Now, the first point is something that they both do. They both attach to receptors. If the neurotransmitter is called an excitatory neurotransmitter, when it causes ion channels to open, it will cause, for example, sodium channels. The key thing there is that sodium channels let a positive ion go into the postsynaptic membrane. If we're talking an inhibitory neurotransmitter, it will cause ion channels to open, but for example, it might cause something that has a negative charge to be the ion channel that opens. Now I mentioned sodium because it's the one we talk about the most, but it doesn't have to be sodium. It could be a different positive ion. So other examples could be things like calcium. So the fact that it's a positive ion is the more important thing here. Same thing on the other side. We're talking about negative things. The theme, though, is what's going to happen to the postsynaptic membrane. If it's an excitatory neurotransmitter, the postsynaptic membrane should become depolarized. That's what happens when sodium enters, causes depolarization. If the neurotransmitter is inhibitory, the membrane will just stay polarized, or it might even be hyperpolarized. So what does that mean if we were to look at numbers? Remember, the resting membrane potential is negative. When the membrane gets depolarized, it gets a positive value. So what we're really saying is an excitatory neurotransmitter will cause the membrane potential to become positive. An inhibitory one will cause it to stay or even become more negative. If the membrane gets depolarized, that says, yes, let's have an action potential. If the membrane is polarized or hyperpolarized, that says no action potential. And then like we labeled on a neuron the other day, the cell body will take the information it gets from all of the dendrites that have receptors and combine the effect. Were there more positive signals or were there more negative signals? If there were more positive signals, the neuron will fire an action potential. If there were more negative signals, it won't. So if positive outweighs negative, we get action, potential, propagation. It will move into the axon and travel without stop in one direction the entire length of the axon to the next axon terminal. These are certainly not all, but some of the more common neurotransmitters that you would hear talked about in terms of body function. Of all of them, like I just said, acetylcholine, you must know about it. The other ones, it's good that you recognize their name and that they are a neurotransmitter, but the mechanism, the way that they work, is more than you must memorize. Sometimes we'll tell you about a neurotransmitter in a question, but all I want is for us to be familiar with basically what each of these neurotransmitters is for. So on page 382 of your textbook, there's this beautiful little table that's there that contains all of them except acetylcholine. So I will fill in acetylcholine, and then I'll give you a few minutes to just sum up the other ones using your textbook. Now, the reason acetylcholine is not in that table is because on the pages prior to that, its function is described in quite a bit of detail. So I'm just going to add in what acetylcholine does. Acetylcholine is the neurotransmitter at a neuromuscular junction. So it causes muscle contraction. Now in the table for the other neurotransmitters, the second column is effects of abnormal production. If there is too much acetylcholine, your muscles would be in this continual state of contraction. So we would have perhaps a muscle cramp or any sort of continuous contraction. It can be as simple as a cramp or as serious as a muscular disorder where muscles can't relax. So what I just did for acetylcholine, what it does and what happens if there's too much of it, is the same thing I'd like you to very briefly fill in for the other 4 neurotransmitters that are there. And like I said, page 382 has a beautiful table that has function and effects. Now in the effects, sometimes it says what happens if there's too much, other times what happens if there's too little. So I'm just looking for one effect of having the incorrect amount of it. It doesn't matter if it's too much or too little. Very briefly sum up dopamine is the one that's involved with movement and pleasure. A lot of drugs, the ones that people are discussing now that are on the next page of the book, have an effect on dopamine. Dopamine makes you feel good, makes you feel happy. If you have too little dopamine, there are a lot of disorders, psychological and otherwise, that could occur. But a lot of them have to do with something that involves movement, like Parkinson's. In Parkinson's, people don't have enough dopamine or dopamine is not doing its job. And that's what makes movement become an issue. If we're talking about serotonin, serotonin has a lot to do with temperature and mood. If you don't have enough serotonin, that is one that's often linked to depression. So serotonin is the neurotransmitter that would get released quite a bit after you have turkey dinner. That's the turkey dinner neurotransmitter. Makes you feel full, makes you feel happy, makes you feel warm, makes you feel sleepy, and not depressed. I don't know how many people feel depressed after eating turkey dinner, but it's because serotonin should be getting released in pretty big quantities. Endorphins are your natural painkillers. Now, if you don't have enough endorphins, of course, your sensation of pain would be increased. But if you look in the book, a decrease or a lack of endorphins has been linked to alcoholism. And the last one, noradrenaline, is the same thing as norepinephrine. Norepinephrine works in tandem with epinephrine, or adrenaline, which is a hormone that gets released by your adrenal glands that helps you respond to stress. So this is the one that has to do with stress. So if you think about your flight or fight response, this is the neurotransmitter that would be involved in that quite a bit. If you have too much of this, you could have things like high blood pressure, and other symptoms of general anxiety or stress. There are a whole bunch of them there, but that's the kind of thing that would happen if you didn't have enough of this, or if you had too much of this, sorry. Now for acetylcholine specifically, there's a little picture on your handout just right next to this little list of neurotransmitters. So we can look at specifically what a synapse looks like when there's acetylcholine there. So here's an acetylcholine synapse. Because acetylcholine is providing the signal between your nervous system and your muscles, this would typically be a muscle, and this would be the presynaptic neuron. If we take a look at what's in the picture, hopefully you can see there are 2 little pieces here, choline and acetyl-CoA. These are the components of acetylcholine. And then acetylcholine here, which is often referred to as just ACH, that's the neurotransmitter. Now, if it was just choline or just acetyl-CoA separately, it won't have the same impact as acetylcholine does. So it needs to get put together. You can see here we have some vesicles that contain the neurotransmitter and that we're representing exocytosis, just like in our regular picture of a synapse. But there's something extra down here. It's a different shape. Acetylcholinesterase ends with ASE, meaning it is an enzyme. A lot of neurotransmitters have this. There is an enzyme that is released at the same time as the neurotransmitter to break down acetylcholine into its components for reuptake. So we said on our typical synapse picture, there's reuptake. This is typically how it will happen. An enzyme, like acetylcholinesterase, it ends with ASE, so we know it's an enzyme, will break down the neurotransmitter so that it stops sending the signal. Then the presynaptic neuron can recycle the components so that it can make more neurotransmitter. Lots of drugs will affect the enzyme that's supposed to break down a neurotransmitter, and that could be the reason that a drug continues to have an effect that is a normal effect for your nervous system, but the drug enhances it or makes it last longer. Now that's the